In this video, we're going to talk about the behaviour of gases. There's going to be combined content and triple content, and I will highlight where the triple content is. But actually, a lot of the time, you'll want to introduce a lot of the elements of triple into combined, even for foundation sets. And I say this because a lot of it is really straightforward, and a lot of it, actually just develops and deepens their knowledge to a point that you would want it at to really understand what's going on with pressure. If you only mention the combined content, sometimes students will have burning questions, or they will know of other phenomenon, but they'll be confused kind of why you're not mentioning. It will all make sense when I start to talk about it. So the first thing for combined is that pressure is proportional to temperature. Now, actually, we don't need to know the maths of this in combined. We only need to know it qualitatively. So all we need to know is that pressure is proportional or directly proportional to temperature. So if the pressure doubles, or if the pressure increases, the temperature increases. If the pressure doubles, the temperature doubles. If the pressure halves, the temperature halves, etc. Okay, we could draw this on a graph. We could show direct proportion. However, this is technically only true if we use Kelvin for the units of temperature. If we use degrees Celsius, we don't get this. If we were to use degrees Celsius, we would actually get a line that looks like this. And the value down here would be absolute zero, which is the lowest possible temperature where effectively all particles stop moving. So we don't need to go into too much detail about this with combined, but they need to know qualitatively this relationship. Possibly even just if pressure increases, temperature increases for foundation level. Now, we can, of course, talk about temperature and volume as well. So it's the same thing. Temperature is proportional to volume, again, if temperature is in Kelvin. So we have the same form of relationship. If temperature increases, volume will increase. And then finally, we have for triple that PV equals a constant. Or we could say P is proportional to 1 over V. So on a graph, we would have this kind of shape, the inversely proportional shape, although it shouldn't actually ever touch the axes. It's a bit of a messy graph. So in triple, they are expected to be able to use this relationship to work out changes. So they might be given a pressure and a volume, and then they would have to work out the new volume at a new pressure, for example. So they do have to use this. It's pretty straightforward. It's all ratios, and typically when doing triple will know the maths from their maths lessons anyway. In terms of combined, I think it's just mentioning these brief relationships. So if temperature increases, volume increases, and if pressure increases, volume decreases, because they all know that, or they will be able to apply that to situations fairly straightforwardly. We could, if we wanted to, combine all of these into one relationship, the ideal gas equation, which is something that we do at A-level physics and also A-level chemistry. So we could say that PV is nRT, where pressure, volume, and temperature. R is a constant, and N is the number of moles of gas. I would only briefly mention this to triple, and I certainly wouldn't be doing any practice questions with it, but it's nice for triple to know where all of these relationships actually lead. Other things that are important is that temperature is proportional to kinetic energy, which we've talked about in another area of this unit, but it's always worth reinforcing this. So if you increase the temperature, then the average kinetic energy of the molecules increases. It's important to say that it's average, and I'll show you a nice simulation in a second that really makes this clear. So one thing that really is a must do in this lesson or series of lessons is to use a simulation. So PhET is really, really useful, phet.colorado.edu. I'll put the link in the video description as well. And there is a gas property simulation. It's worth having this up on a board for maybe 10, 15 minutes, talking through it, looking at the different options, because it really makes things clear. So the first thing is we can make clear, what is pressure? Pressure is the collision of particles with a surface. And we should be reminding students that pressure is force over area, which they will have done at Key Stage 3. This isn't technically mentioned at GCSE, but it's assumed knowledge. So in terms of gas pressure, it is the force of particles hitting a surface that causes the pressure. So more collisions gives us a higher pressure, or molecules moving faster gives us a higher pressure. At triple, in the mechanics unit, we will look at this relationship where we say force is mv minus u over t. So force is mass times acceleration. Acceleration is v minus u over t, and then we can expand out the brackets to mv minus mu over t. So force is the rate of change of momentum. So if an object's momentum is changing, then there is a force. So there's an increase in pressure if we either increase the mass of our particles, or we increase the change in velocity, or we decrease the time. And of course, increasing the temperature will increase the kinetic energy and therefore increase the velocity, because kinetic energy is, of course, half mv squared. So I would only really go into this amount of detail with triple, but certainly everything in words that I've just said is important for combined for their understanding. A little bit more information to make students think. If we had a particle moving and then it stops, that's a smaller change of momentum than if that same particle rebounds, because we've had to stop its velocity and then make its velocity go in the negative direction. And then something like this, again, has a relatively small change of momentum, because we're only really deflecting its direction a little bit. So it's always nice to kind of make students think of different scenarios. So this simulation is incredibly useful. So we can do a lot with this, which is why I say it's worth having up 10, 15 minutes. We can, for example, increase the temperature, and then we will see what happens to the pressure. So if you look at the dial on the screen, you'll see the pressure going up, and over a period of time, we will start to see the molecules increase in speed. Although actually that's sloppy language, and we should be very clear with students. Usually what I do is use sloppy language, and then I'll say, well, actually, what mistake am I making here? Why is it wrong to say that the molecules are not moving faster? What am I missing? I think it's sometimes good to make these mistakes if they're deliberate, because then it encourages students to really think about, what's going on. So, of course, if we just cut it down a little bit, we can see that some molecules move really fast, some moving slow, and there's a range of speeds, based on the collisions and based on the random motion. So we can, if we go on the energy tab, you can get these nice graphs which show the number of particles against their speed and their kinetic energy. We can see that this follows the Maxwell-Boltzmann distribution, which is not needed at GCSE, but that's what the distribution is, and we can see what the kinetic energy of particles is doing. So most are kind of down here, but there's a few moving, with really high velocities at any time. And it will tell us, of course, what the average speed is here as well. We can also, challenge students. We can talk about, the fact that if we looked at the velocities, what would the average velocity of everything be? It'd be 0, because some are moving with a positive velocity, some are moving with a negative velocity. Overall, they cancel, because velocity is a vector, speed is a scalar. So it makes more sense to talk about scalars. if you've got a really able set, then those math statistics, you can talk about the analogies with standard deviation, about squaring something and square rooting it to get rid of the minus signs. If it's a lower set, I probably wouldn't bother with that so much. I would just do it all in words with positive and negative values. So we can also do things like change the volume. And in this case, when I've decreased the volume, I've increased the pressure so much, I've just blown the lid. But obviously, if we change the volume, you'll see what happens to the pressure. It increases. You will see that the molecules move faster on average. You could, if you wanted to, open the lid and you can see what happens to the pressure as particles start to leave. We can add more molecules, and then we can see that we're going to have more collisions in a fixed time, therefore the pressure increases. We could, if we wanted to, add a second lighter element and see what happens. Let's return the lid. And then to link this to collisions, and students do need to be able to explain maybe 2 or 3 mark questions in terms of words, we can actually put on a collision counter, and we can count the collisions in a fixed period of time. We could time 30 seconds, for example, or here it's 10 picoseconds according to their scale, and then we can make a change. So for example, we could change the volume, and we could record the collisions again, and we'll see the vast difference in collisions, and we can really link pressure to collisions. And then we could obviously do the same with heating, with cooling, etc. The other thing this does really nicely is we can model diffusion, which is not really something that would talk too much about GCSE physics, but for chemistry, this is just as good. So you can play around with the masses, the number of particles, the radius of particles, for example, and then you can remove the divider and you can see how the particles diffuse, how they start to mix. And you can have some really nice discussions here about pressure, about the rate of diffusion based on these variables. And yeah, this is a really good simulation. You can spend a lot of time with this. And if students ever forget what's going on, if you set them a series of questions, if you have a simulation like this on the board, you can constantly refer back to it, and you can go really imagine the particles, what they're doing, and students do generally get what's going on. The last few things that are worth mentioning. This topic is great because there's loads of nice either demos or everyday objects that we can talk about that really make these ideas clear. So if we want to discuss pressure and temperature, we can talk about heating a deodorant can. And of course, as the temperature goes up, the pressure goes up, and eventually, the whole thing will explode. And students know this, and we've seen that from the simulation. But also the reverse, which students find harder to accept sometimes, that actually with a deodorant can, if we spray it, what happens to the outside of it when students' hands are on it? It gets cold. Why does it get cold? Well, we've actually decreased the pressure by letting the gas particles out. So if we decrease the pressure, what happens to temperature? It goes down. And then you can link this to the fact that, where does the energy come from to expand these gas particles to make them occupy this larger volume? Well, it obviously comes from our hand. So our hand is actually providing the energy to these gas particles, and therefore our hand gets cold. In terms of temperature and volume, we've got a couple of different options. We can get a flask, and we can attach a gas syringe to it, and then we can heat it with a flame. And as we heat the air in here, we will expand the gas syringe. And if we cool the air by putting it into a beaker of ice water, then of course the volume will decrease as the temperature decreases, and here obviously the volume increases as the temperature increases. So this is a nice example. We also have something called a fire piston, which is a piston and you put a little bit of special paper at the bottom, and then you rapidly decrease the volume, that makes the temperature go up, and then the paper will set on fire. So that's worth showing to students. You probably need to under the visualizer because it is quite a small item. The other thing that all students will know, and this is a really good example, is if we have a tyre and we have a pump, as we pump up the tyre, so as we decrease the volume and increase the pressure this time, what happens to the temperature? The temperature goes up. Now, this is potentially a slightly harder explanation because we're talking about decreasing the volume. Why isn't the temperature going down? Well, actually, we're increasing the pressure. So we're really linking it to this over here. But we're only doing this with words, we're not doing it with math, so it doesn't really confuse students too much. And obviously, why does it heat up? Well, we've just said the pressure is increasing, but also we are providing energy. We are doing work on the gas. So formally for triple, we should be talking about doing work on the gas. For combined, we can just talk about we're providing energy. We're with our hands squashing the gas, and obviously that energy is going into its temperature. But in terms of triple, we need to talk about doing work on the gas, heating it up, or if the gas does work. So here, the gas does work, so the temperature decreases. But like I said, this is triple. And then we have also got a couple of nice things for pressure and volume, which are worth showing to students even in combined because it's nice demos and they really like it. We've got the vacuum chamber, which is a bell jar attached to a pump. And then you can put different objects in it. So, for example, like a balloon. And then obviously, if you decrease the pressure, what happens to the volume of the balloon? Of course, it's going to increase. There's also a can crush demo. There's some nice videos of people doing this with oil drums or with even a whole tanker. But the can crush on its own is impressive enough. So what you do, you get yourself a Bunsen burner, and you get a can with a tiny bit of water in the bottom. This is crucial. When you heat it up, the water boils very quickly because you've only put a couple of millimeters in there, and we've got steam inside the can, and importantly, no air. Then quickly, and this does take a little bit of practice, you're going to put it into some ice water upside down. So what happens? All of the steam condenses back to its original amount of water. What have you been left with? You're left with a vacuum. And now we've got the air pressure outside. It's going to push the can, and you see very, very rapidly, within, a fraction of a second, that the can itself is a fraction of its volume as the air pressure pushes. So this is a nice way to reinforce the air pressure pushes. Vacuums don't suck, air pressure pushes. And so the high air pressure from the outside is pushing in on the vacuum, and in a vacuum there's nothing to push back, therefore the can crushes. There's so many other fun air pressure demos that you can do when you've got a high pressure and a low pressure. You can search for these on YouTube as kind of a fun extension, but this one is really a must-do. It reinforces this concept. It reinforces this relationship, and it really gets students to think about the particle model as well, because we're talking about vacuum compared to outside where there is a pressure.